Hello and welcome to this new video. In this video, I'm going to solve the first 6 exercises of chapter 1. So let us start with the first exercise. In a certain country, there are no two consecutive sunny days. If one day is sunny, the next day can be rainy or snowy with equal chances, so 50%, 50%. If one day is rainy or snowy, there is 50% chances of weather change, so 50% of no weather change the next day. And if there is weather change, there is 50% chances that the weather will be sunny. So this makes 25%. Model the situation by a Markov chain and determine its transition matrix. First question. Second question, if someday is sunny, what is the most probable weather 2 days later? And third question, determine the communication classes of this chain, the recurrent classes and their period. Okay, so it's clear that we have 3 states. We can call the snowy state by 0, the rainy state by 1, and the sunny state by 2. Okay, so it's clear that we have a Markov chain. So the state of the weather at day n will be a Markov chain, or will be the value of the stochastic process at time n. And now from state 0, from snowy to snowy, we said that we have 50% chance of change, 50% of not change. So it's from 0 to 0, it's 1/2. From 0 to 1 to 1, it's 1/4, and from 0 to 2, it's 1/4 again. So, and the second row is similar. And now, if we are in the sunny state, then we cannot. The next day cannot be sunny. So therefore, with equal chances, the day will be either snowy or rainy. So 1/2, 1/2, 0. Okay, this is the assumption. So this is the first. Of course, you can draw the transition graph. It's very easy. Now, to answer the second question, we need to find the biggest among the probabilities P202, P212, P222. Okay, and here we have 2 ways of proceeding. So either we compute P squared, and these numbers will be the elements of the third row. If we compute P2, we find this result. Just do it. And therefore, these probabilities are 1/2, 1/4, 1/4. So the most probable case is actually snowy, P20. These are conditional transition probabilities from state 2, from the sunny state. The second method requires less computations, but it's the same idea. We use the Kolmogorov-Chapman equations, and here actually we include the Kolmogorov-Chapman equations are included in these computations actually, but here we focus just on the third row. Instead, we don't need the first 2 rows. So when you do the computations, you can check that there are 1/2, 1/4. We don't need to compute the third one actually, because we know it's 1/4 because they sum to 1. So it's just enough to compute 2, and we get the same conclusion. Okay, so the times should be here. Okay, and third question, period and classes. We observe that we have a cycle, a Hamiltonian cycle, 0, 1, 2, 0, as you may check from the graph or from the matrix actually, because we can go from 0 to 1, from 1 to 2, it's positive, and from 2 to 0 again. So this is a cycle through all vertices or all states. Therefore, all states communicate. Whenever we find a cycle passing through all states, whether Hamiltonian or not, we conclude that all states communicate. And therefore, there is only one class, so the chain is irreducible. Therefore, we can conclude 2 things. All states have the same period, so it's enough to determine the period of one of them. And this is easy because if you look at 0, P00 is positive. So, and we know that, so 1 is in the set J0, and therefore the period is 1. Okay. So all states have period 1. Okay, and now to see that all states are recurrent, we can argue in 2 ways. and we'll not repeat this every time, just one time. So first way of seeing that all states are recurrent, we know that every finite Markov chain has at least one recurrent state. And recurrence is a class property. So if one state is recurrent, all the class is recurrent. So since there is one class here, so all states are recurrent. Okay. And second way, if you look at the graph, you will convince yourself that there's no way of leaving state 0 and never coming back. Okay, because if you it's easier to look at the transition, but you can also look at the diagram. So what are the possible states of leaving 0? From 0 can go to 1 or to 2. If you go to 1, we will certainly or to 2, we will certainly come back to 0 later. Okay, with positive probabilities. So there is no way of escaping 0, and therefore 0 cannot be transient. Okay, so it's recurrent. Okay, next exercise, very easy. We did something similar in class. We have a two-state Markov chain with this transition probability. We have to find the condition probability in 3 steps from moving to 0 to 1. And once again, you have 2 ways. So we need to compute P013. First way, we compute P to the 3. So it will take some time, of course, if you want to do all these operations by hand. But you can use the calculator, of course. And by the way, in the exam, you are allowed to use the calculators. So P01 is this guy here, 109 over 216. Okay. Or you can use you can apply directly the Kolmogorov-Chapman equations, okay, and you get the same result. Now, the second method is usually less expensive in computations, okay, because you can count the number of operations involved here. So you count them and you can compare, okay. So when I ask you only about some specific transition matrix and you don't have enough time, it's better to use the Kolmogorov-Chapman equation. But this has the advantage of being more clear, okay, because you may be lost in these computations here. But essentially, they are the same, because the fact that P013 is this element of P3 is actually relies on the Kolmogorov-Chapman equations, as we know. Okay, so it's essentially the same idea, but the difference is that in the second method, we only concentrate on one entry, whereas in the first method, we need to compute all entries. So this is why they take more time. Okay. Third exercise, we have a random walk on a circle. So we have 5 states on a circle, and each one is connected to its neighbors. Okay, so and at each time step, a walk can move from a state to its neighbor. So from 0 can go to 1 or to 4, from 1 to 0 or to 2, and so on. So of course, this is a Markov chain, and it's easy to find its transition matrix. So here actually with equal probabilities. So the probabilities are all 1/2. Okay, I didn't throw them here, but 1/2, 1/2, 1/2, 1/2. So this is the transition. From 0, we can either go to 1 or to 4, right? Because 1 and 4 are the neighbors of 0. From 1, we can either go to 0 or to 2. Okay, and so on. From 2, you can either go to 1 or to 3. From 3, you can either go to 2 or to 4. And from 4, you can either go to 0 or to 3. All right, so this is the transition matrix. And now, second question, we have to determine the communication classes. So once again, you have Hamiltonian cycle, for example, it's just a circular path, 0, 1, 2, 3, 4, 0. So this is a Hamiltonian cycle, and therefore all states communicate. So the chain is irreducible. So it's enough to determine one, and of course, once again, the chain is recurrent, of course. So all states are recurrent, by the same argument as before. And if now the less trivial question, so this is trivial. The less trivial is determining the period of state 0, for example, or any other state, because they are just symmetric. So if we look at the path 0, 1, 2, 1, 0, okay, on the graph, 0, 1, 2, 1, 0. It's a path, it's a loop, it's a cycle from 0 to itself in 4 steps. So 4 belongs to this to J0. And if you look at 0, 1, 2, 3, 4, 0, this is a cycle in 5 steps. So we conclude that 4 and 5 are both in J0. Okay. So when I write this, it means that P004 is positive, and this means that P005 is positive. So 4 and 5 belongs to J0. And we conclude that the greatest common divisor is 1, because we have 2 consecutive integers in the set. So D0 is 1, and therefore the chain is aperiodic. Okay, it has period 1, so it's irreducible and aperiodic. So it's ergodic, if you like. Okay, exercise 4. It's the modeling problem. Okay, not totally trivial. So, but it's interesting. So the Smiths receive the paper every morning and place it on a pile after reading it. Each afternoon, with probability 1/3, someone takes all the papers in the pile and puts them in the recycling bin. Also, if ever there are at least 5 papers in the pile, Mr. Smith, with probability 1, takes the papers to the bin. Consider the number of papers in the pile in the evening. Model the situation by a Markov chain and determine its state space and transition matrix, and then determine the nature and period of each state. Okay, now this is not completely trivial, so we have to really understand the problem. And I suggest that so we have 5 states actually. So according to the number at the evening of day n, right? So the number of the papers in the pile at the end or at the evening of each day, we have just 5 states: 0, 1, 2, 3, 4. Okay, we cannot reach 5 actually, okay, as you shall see now in a moment. So we can draw this table. Okay, suppose now this is at evening of day n. Okay, suppose that there's no paper in the pile. Then the next morning they will receive a new paper, right? Same, it will be in the afternoon one. So just before one of the Smiths put the paper in the recycle bin. Okay, so there's a redundancy here. So next morning and next afternoon, just before. So in the evening, if one of the Smiths takes the paper to the recycling bin, there will be 0, right, in the evening. This happens with probability 1/3, right? Now, if no one takes the paper, it will remain. So in the evening, it will be 1. So from state 0, we can either remain at state 0 with probability 1/3, or we can move to state 1 with probability 2/3. These are the only possibilities. And you repeat this reasoning. If there is 1 paper in the pile, the next morning it will be 2. So just before one of them puts it in the recycle bin, it will be 2. If one of them takes the paper and put it in the recycle bin, there will be 0 in the evening. And this happens with probability 1/3. And if no one takes the paper, then it will remain at its place. So it will be just 2. And this happens with probability 2/3. So from state 1, we can either go to 0 or to 2. From state 2, same thing. Okay, so if we have at the evening of some day 2 papers, the next morning they will be 3, in the afternoon 3. If one of them puts the paper in the bin, there will be no paper, so it will be 0 with probability 1/3, or with probability 2/3 it will remain. And same thing for 3. So 3, 4, 4, 0 or 4. So from state 3 we can either go to 0 or to 4. And now suppose that we have 4 papers, then the next morning it will be 5. In the afternoon it will be still 5. And we know by the assumption that with probability 1, Mr. Smith will put everything in the recycle bin. So we go to state 0 back with probability 1. Okay, so therefore we have this transition matrix from 0 to 0, 1/3, from 0 to 1, 2/3. From 1 to 0, 1/3. So just I'm reading this. So, and from 1 to 2, 2/3. 2 to 0, 1/3. 2 to is 3, 2/3, and 3 to 0, 1/3, 3 to 4, 2/3, And from state 4, we can only go back to state 0's probability 1. Okay. And of course, you can easily draw the transition graph of this matrix. Okay, so this was, okay, now the nature and period, let us see. So this is the graph. Okay, so from 0, we can go either to 0 or to 1. From 1 to 0 or to 2. So I put 0 in the middle actually, because 0 is the most connected state. Okay, so but you can draw it in another way. Okay, so and all states point to 0 actually. Okay, so this is the transition graph, and now it's easy to see that to find one Hamiltonian cycle, 1, 2, 3, 4, 0, 1. Okay, so all states communicate, and therefore the chain is irreducible. And now, since it's a finite chain, there is all states are recurrent, and the period of 0 is 1 because P00 is positive. It's 1/3. So it's an irreducible aperiodic chain. Okay. Fifth exercise, 3 black balls and 3 white balls are placed in 2 urns such that each urn contains 3 balls. At each time step, we choose randomly a ball from each urn and we exchange the 2 balls. Consider the number of white balls in the first urn, model the situation by a Markov chain, and determine its transition matrix. So once again, this is a modeling problem, okay? And it's very important to you, if you want to work in applications later, it's very important to be able to see Markov chains, to model situations with Markov chains. Okay, it's not just, so the course is not just about computations and proving theorems, it's also about modeling. Okay, so here the number, why is it the Markov chain? Because we have 4 possible states. Okay, if you have 3 balls in an urn, in the first urn in this case, there could be 0 white ball, 1 white ball, 2 white ball, or 3 white balls. So we have 3 states. Okay, and then we can move from one state to another according to certain properties that we will compute now. Okay, so it should be clear that we have an object moving between 4 states. Okay. So, so state 0 is, this is the, so what do we mean by state 0? It means that the first urn contains 3 black balls, so 0 white, and therefore all the whites are concentrated in the second urn. So I will denote this situation by BBB WWW. Or you can draw, if you like, 2 urns with 3 black balls here and the second urn 3 white balls here. And now we want to exchange. And state 1, we have in the first urn 2 black, 1 white. Okay, so 1 white is corresponding to the number 1. And the second will necessarily contain 2 white and 1 black. State 2, 1 black, 2 white, and vice versa for the second urn. So there's a redundancy here. And state 3 is just the opposite of state 1, a 0. So we have 3 white and 3 blacks in the second urn. Okay. Now, so I hope that you are convinced that this is a Markov chain on 4 states. But the problem now is to determine the transition probabilities. How can I move from 0? Where can I go? I cannot go from 0 to 3 actually, but I can go to 1. From 1, I can go either to 0 or to 2 or stay at 1. From 2, I can either go to 1 or to 3 or remain at 3. And 3, I need to go to 2. Okay, so let us put all these informations in a table. Okay, consider state 0. So we have the composition is black, black, black for the first urn, white, white, white for the second urn. Okay, now when we choose one ball from the blacks, so this happens with probability 1 actually, so because all are black, we choose one ball from the whites from the second urn and we exchange them. So the next composition would be black, black, white necessarily, and the second urn will contain white, white, black. There's no other possibility. And this happens surely with probability 1. Black, black, white, 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 black is just state 1 because we have just one black, one white here. Okay, so from state 0 we can only go to state 1 with certain probability, with probability 1. Okay, now from 1 it becomes more interesting because now we have 3 options or 3 possibilities. If we choose the white in the first urn and the black in the second urn and exchange them, the situation will be black, 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 white, 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 and this is just state 0. So we can move from state 1 to state 0, but what is the probability of transition? Okay, what is the probability of choosing the white? There's only white, but there are 3 balls. So the probability of choosing the white is 1/3 here. The probability of choosing the black in the second urn is also 1/3. But since they are independent, the probability is just the multiplication. So the probability of from this configuration to this configuration is just 1/9, 1/3 times 1/3. Okay, so this is elementary. Now, but this is not the only possibility. Suppose that, okay, what happens if we still are in the same state? So how to move from BBW WWB to BBW WWB? So same configuration. We have, this happens in 2 ways. Either we exchange this white with one of these 2 whites, so we exchange the whites, so the configuration does not change. So since there is only one white in the first urn, so the probability of choosing it is 1/3, and there are 2 whites, so the probability of choosing them is 2/3. So this is the first possibility. Or we exchange one of the black here with the black here, and the situation is completely symmetric. The probability of choosing one black in the first urn is 2/3, and the probability of choosing one black is 1/3. So I just add the 2 probabilities because the events are disjoint. And I get finally 4/9. So 2/9 plus 2/9. And the third possibility is to exchange one black with one white. And okay, right? So I can move from state 1 to state 2 by exchanging one black in the first urn with one white. Since there are 2 blacks, the probability of choosing one black ball is 2/3. And the probability of choosing one white from the second urn is 2/3 as well. So the product is 2/3 times 2/3 is 4/9. And that's it. These are the only possibilities. So from state 1, I can go either to state 0 or to state 1 or to state 2. Okay, so this is just elementary probabilities. And I repeat the reasoning. From state 2, there are also 3 possibilities. And if you think of them, you will find you can go from state 2 to state 1 by exchanging one white with one black. So this happens with probability 4/9. You can remain at state 2. How do we remain? We have to either exchange black with black, so 1/3, 2/3, or one white and one white, so same thing. And if we want, so we can move from 2 whites to 3 whites in the first by exchanging this ball with this white, and this happens with 1/3 times 1/3 is equal 1/9. And finally, from state 3, we necessarily have to move to state 2 because we exchange one white with one black. So it's, if you like, 3/3 times 3/3. So it's 1. And that's it. So if you put, we can now put everything in one matrix. So the transition matrix is 0, 1, 0, 0. From 1 to 0, 1/9. From 1 to 1, it's 4/9. From 1 to 2, it's 4/9. From 2 to 0, there's no way. From 2 to 1, 4/9. From 2 to 2, 4/9. And from 2 to 3 is 1/9. And from 3 to 2 is 1. And that's it. So this is this solves the problem. Okay. Last exercise. We are given a homogeneous Markov chain on 5 states with a certain transition. We have to determine the period of each state. Okay, so let us first draw the transition graph, but I didn't put the probabilities, just the arrows to. So when I put arrows, it means I have a positive probability. So this is, you can, so from 0 I can go to 1 and 2. From 0 I can go from 1 to 1 and 2. It's very important. From 1 I can go to 3 or 4. From 1 I can go to either 3 or 4. From 2 I can go something to 3 or 4. And from 3 and 4 I can only go to 0. 4 and 3 go to 0. So that's it. This is the transition graph. Now we can check here, of course, that this is irreducible, because you may find one cycle, but it doesn't have to be Hamiltonian. So I can go, for example, 0, 1, 4, 0, 2, 3, 0. That's it. So we have a cycle. So the chain is irreducible, but determining the period is not clear. Okay, so this is why here, because the graph is small, I can draw a tree representing all the possible paths from 0 to itself. So I will do it. All right. So from 0, where can I go? From 0, I can go to either 1 or 2. First step. Now, from 1, I can go to either 3 or 4. From 2, I can go same thing, 3, 4. And now, from 4 and 3, I can only go back to 0. And that's it. So what does this mean? This covers all the possibilities. So this means I cannot go from, there's no path from 0 to itself of length 1, and neither of length 2, but there is several paths of length 3. Therefore, and then the chain will repeat itself, right? Because from 0, I can draw a similar tree. And from the 0, so it's kind of fractal set, if you like. So the first conclusion is that P003 is 1. So with probability 1, I will go necessarily with probability 1, I will go from 0 to itself in 3 steps, no matter what is the path I've taken. So it could be 0140 or 0130 or 0230 or 0240. And therefore, what follows from this tree actually here is that 3, 6, 9, etc. So J0, if you like, is composed of 3, 6, 9, 12, etc. So the period of 0 is necessarily 3. And therefore, since the chain is irreducible, all the states have the same period. Okay, and of course, I could have drawn a tree starting from 1, because I can continue, right? So this is an irreducible chain of period 3. Okay, so this concludes this video. Thank you for your attention. In the next video, I'm going to solve the remaining exercises.